Welcome to the Explainer. When you look up at the night sky, it's so easy to picture the Milky Way as just the static, peaceful, majestic pinwheel floating out there in the dark. But the reality, well, it's completely different. Today, we're going to look at our home galaxy not as some tranquil spiral, but as this highly dynamic, ever-growing beast with a deeply violent, literally cannibalistic history. We're going to explore how scientists are uncovering this hidden past by studying some of the absolute most delicate, beautiful structures in the cosmos.
Okay, let's dive right into this. So, for a long time, we thought the fringes of our galaxy were pretty much empty. But recently, astronomers have spotted these faint, incredibly long rivers of stars stretching all the way across the galactic halo. And these aren't just random alignments, right? These faint rivers are acting as the ultimate fossil records of the cosmos, and they hold the key to a massive galactic mystery. Because what we're actually looking at here are the shredded remains of completely different galaxies and star clusters that just ventured a little too close to home.
Astronomers actually call this process galactic cannibalism. I know, it sounds intense, and honestly, it is. But it's a core part of the hierarchical model of galaxy formation. Basically, massive galaxies like our Milky Way don't just pop into existence fully formed out of nowhere. They grow over cosmic time by accreting or swallowing up lower mass satellite systems. And these stellar streams, they're very different from the thick, gaseous spiral arms, or those transient tidal tails you see when giant galaxies merge. When smaller dwarf galaxies or globular clusters orbit too close, they just get ripped apart. You can really think of these delicate streams as the precise forensic evidence left behind at a cosmic crime scene. They prove exactly how our galaxy was built, piece by piece.
So, how exactly does a compact cluster of stars turn into a massive river? Well, it all comes down to orbital mechanics and tidal disruption. First, a smaller system approaches the Milky Way. As it gets closer, the differential gravity, the tidal forces of our massive galaxy, begin to pull way harder on the near side of the cluster than the far side. Once these external forces completely overwhelm the cluster's own internal gravity, that's the beginning of the end. Stars actually start to escape through these invisible gravitational doorways we call the L1 and L2 Lagrange points. And finally, because the cluster is continuously moving, the stars spilling out of the front form a leading arm speeding ahead, while the stars spilling out the back form a trailing arm lagging behind. It permanently traces the exact orbital path.
There's a quote that brilliantly illustrates the physics at play here. Oleg Gnedin, an astronomer at the University of Michigan, describes the process perfectly. He says, "It's like riding a bike with a bag of sand, only the bag has a hole in it. Those grains of sand are like the stars left behind along their trajectory." I love that analogy because it shows it's not some sudden explosion, right? It's a slow, inevitable leak that plays out over billions of years, just gently laying down this cosmic breadcrumb trail. Now, you might be wondering, do all these victims of galactic cannibalism look the same? Definitely not. The original mass and the internal temperature of the doomed system dictate the exact shape of the resulting stream. So, if the progenitor was a globular cluster, which is basically a tightly packed, relatively low-mass ball of stars, the resulting stream is what astronomers call dynamically cold. It's incredibly narrow and thin. It's almost like a precise pencil line drawn right across the sky. On the flip side, if the victim was a dwarf galaxy, which has a lot more mass and a higher internal velocity dispersion, the resulting stream is dynamically hotter. It appears much broader, way more dispersed, and structurally complex. Now, what's really interesting about this is how we actually prove these widely scattered stars belong together. Notice the chemical fingerprint mentioned here. This represents what astronomers call cosmic DNA. Because these streams are so impossibly faint, picking them out from the billions of normal foreground stars is incredibly tough. But the metals in a star form an almost direct link back to its birthplace. Elements produced by supernovae or heavier neutron capture elements like barium and europium act just like a chemical fingerprint. By analyzing these chemical abundances, we can confidently link scattered stars back to the exact same dead progenitor galaxy, even if that galaxy was destroyed billions of years ago. It's pretty amazing. All right, moving on to Section 1, detecting the invisible rivers. Because obviously, knowing these streams exist and actually finding them are two entirely different things. So let's transition from the violent history of our galaxy to look at the modern, high-tech algorithms and space missions that astronomers are currently using as their cosmic magnifying glasses. Take a look at this map. It reveals 26 distinct stellar streams plotted across equatorial coordinates. Finding these was made possible largely by the European Space Agency's Gaia mission, which provides precise 6D kinematics.
Basically, that means we know exactly where billions of stars are and exactly how they're moving. But data alone isn't enough, is it? Researchers use incredibly powerful software, like the Streamfinder algorithm, to actually parse this massive data set. It statistically tests millions of possible orbits to bridge the gaps and reveal these hidden, co-moving groups of stars against a really dense, chaotic background.
We are absolutely in a golden era of discovery for this stuff. Gaia's astrometric data, complemented by targeted observations from powerhouses like Hubble and the James Webb Space Telescope, it changed everything. Algorithms like Streamfinder evaluate the likelihood of stars moving along coherent orbits. And more recently, another algorithm called StarStream, developed over at the University of Michigan, used physics-based particle spray modeling to automatically discover 87 new stellar stream candidates. 87! Plus, facilities like the Dark Energy Spectroscopic Instrument, or DESI, are now stepping in to provide the critical radial velocities and metallicities we need to chemically confirm these structures.
Let's move on and see how this builds as we enter the Evidence Room, Section 2, Famous Rivers of Stars. We're going to examine 3 of the most famous and extreme stellar streams currently wrapping around our galaxy.
First up is the GD1 stream, and the number you need to remember here is 100 to 1. That's its extraordinary length-to-width ratio. GD1 is just a perfect example of a globular cluster stream. It extends a massive 80 degrees across the northern sky, yet it is astonishingly narrow, only about 70 parsecs wide. Because its stars are so chemically uniform and tightly clustered together, we know for a fact it originated from a single globular cluster that dissolved within the last 3 billion years. It's essentially a razor-thin ghost ship sailing through the galactic halo.
But then, we have the absolute behemoths. The Orphan Chenab stream stretches an unbelievable 200 degrees across the sky, wrapping from the northern all the way to the southern hemisphere. Then there's the famous Sagittarius stream. This one originated from a dwarf galaxy that has actually punched right through the Milky Way's disk multiple times. And those impacts didn't just rip Sagittarius apart. The data shows the resulting shock waves actually triggered massive star formation episodes in our own galaxy. Finally, there's C19. This one is extremely metal poor, which points to a very ancient origin, but it's kinematically hot, with a surprisingly high velocity dispersion, which completely challenges our traditional models of how these streams should behave. Which brings us to perhaps their most profound application in Section 3, unmasking dark matter. We're shifting gears here from mapping the visible remnants of dead galaxies to tracking something completely invisible, dark matter itself. To really grasp this, we first need to define what a dark matter subhalo is. According to our leading cosmological model, lambda cold dark matter, the dark matter halo surrounding our galaxy isn't perfectly smooth. Not at all. It should be absolutely teeming with smaller, dense, completely starless, compact clumps of dark matter called subhalos. Now, because they emit absolutely zero light, they are completely invisible to our telescopes, but they still have gravity. So the crucial point is, how do you catch an invisible culprit? Well, you look at the scars it leaves behind. When one of these massive, invisible dark matter subhalos punches right through a delicate, razor-thin stream like GD1, its gravity kicks the stars out of alignment. And this leaves permanent physical fingerprints. We see unexplained density gaps, where stars were literally scattered. We see overdense stellar spurs extending outward from the main track. We see a permanent increase in the velocity dispersion, meaning the stream gets hotter and wider after the encounter. We even see cumulative tidal distortion, fanning out the shapes over billions of years. Basically, these streams are acting as giant, galaxy-sized tripwires for dark matter. To actually prove these gaps are caused by dark matter, scientists literally have to rewind the clock. By using advanced N-body simulations and particle spray algorithms, researchers can computationally model the exact formation of a stream over billions of years. They inject simulated dark matter subhalos right into the computer model, and then just watch the gravitational encounters play out. When the simulated damage matches the exact gaps and spurs we observe in reality, boom, we can effectively map the mass, location, and abundance of the invisible dark matter hidden right here in our galaxy. We've learned a staggering amount in just the last few years, but honestly, the hunt is really just getting started. Let's head into Section 4, the future of stream hunting, and look at how next-generation observatories are going to expand our view way beyond our local neighborhood. The upcoming Vera C. Rubin Observatory is going to be an absolute game-changer. It's going to push our detection capabilities to the very distant outskirts of the Milky Way's halo. And this is huge because out there, the streams are totally free from the chaotic gravitational interference of the Milky Way's central disk. It allows us to study dark matter interactions in near-perfect isolation. We're also looking further outwards. Recently, a staggering 163,000 light-year-long stream was discovered around the giant spiral galaxy M61. When you combine that with upcoming kinematic follow-ups from the Nancy Grace Roman Space Telescope and the massive capabilities of the Square Kilometer Array, we are on track to build a totally comprehensive map of how galaxies assemble and how dark matter behaves across the entire universe.
It is such a beautiful paradox, isn't it? That the smallest, faintest, most delicate rivers of dying stars in our galaxy are currently our most powerful tool for mapping the universe's most massive invisible structures. It completely reshapes our understanding of the Milky Way, from a peaceful spiral to this dynamic, living system shaped by mergers and invisible forces. And it leaves us with a thrilling thought. If we can use faint light to trace the invisible dark matter that holds everything together, what else is hiding out there in the dark, just waiting to be eliminated?